All right, let's dive into the wild world of quantum computing. But today, we're not just talking about the amazing hardware, we're talking about the software, the classical brains that are actually telling these super powerful machines what to do. This is going to be fun.
I mean, it is an absolutely incredible time to be watching this space. The number of qubits, the basic building blocks of these machines is just skyrocketing. We're seeing devices blow past 100, 200, even 1,000 qubits. The hardware is scaling up like crazy. But all that growth brings up a really important question.
Because here's the catch. You don't just sit down and program a quantum computer directly. Nope. You use classical software on a totally normal computer to build and fine-tune the quantum programs. And that classical step, it's becoming a massive performance bottleneck. It's basically a giant traffic jam on the quantum superhighway.
And look, this isn't some problem for the future. It's happening right now. As the quantum hardware gets bigger and better, the classical software is really struggling to keep up, and it's creating some serious growing pains for the whole field.
How serious? Well, take a look at this number, 1.4x. What in the world does that even mean?
Yeah, you heard that right. For the really complex jobs, the thinking part, the compiling on a classical computer, can take way longer than the doing part running on the multi-million-dollar quantum computer itself. Just think about that. It's like telling an Olympic sprinter to wait at the starting line for 2 minutes while you spend 3 minutes tying their shoes. That is exactly the kind of problem we're facing.
So what do? How do we get this software into shape? Well, the very first step is to create a standardized way to measure its performance, a universal fitness test, if you will.
And that is precisely what a team of researchers went and built. It's called bench press. Honestly, the best way to think about it is like the NFL Combine, but for quantum software. It's this open source set of tests designed to push these software packages to their absolute limits and see how they really perform under pressure.
And we're not talking about a quick jog around the track here. Bench press is incredibly thorough. For every single software package it looks at, it runs a massive 1,066 different tests. This is a deep dive into what these things can actually do.
So these tests, these drills, are broken down into 3 key areas. First up, circuit creation. How fast can the software build a program from scratch? Simple enough. Second, manipulation. How quick is it at changing or transforming that program? And third, transpilation. Okay, this is the big one. This is about how well it can take an abstract idea for a program and optimize it to run on a specific, real-world quantum chip with all its messy, real-world limitations.
And bench press is tracking a few key things here. Speed, of course, that's huge. But it's also measuring the quality of the final program. It looks at stuff like gate count and circuit depth, which are basically just stand-ins for how likely the program is to fail. See, in the noisy world of today's quantum computers, every extra step is another chance for an error to sneak in. So shorter, more efficient circuits are almost always way better.
Okay, so we've got our fitness test, we've got our drills. Who are the athletes? Let's meet the contenders who stepped up to get put through the bench press ringer.
The study put 7 major software development kits, or SDKs, to the test. These are the toolkits that scientists and developers are using every single day. You've got heavy hitters from Amazon and IBM, with Qiskit and its cloud service QTS, plus a bunch of other really powerful open source projects like Cirq, BQskit, Stack, and Tkit. Now, here's a really important thing to remember. These SDKs are not all built to do the same thing. Some, like Qiskit, are kind of like the decathletes of the group. They're all-rounders designed to do a bit of everything. But others are specialists. Stag, for instance, is pretty much just a transpiler. It's a sprinter that focuses only on that last, super hard optimization step. And that variety is a huge part of this story. So the stage is set. The athletes are at the starting line. How did they actually do? Well, this is where things get really interesting, because you start to see these fascinating trade-offs between speed, quality, and what each tool can do.
When it comes to just pure, raw speed, one SDK just left everyone else in the dust. Stake was the undisputed speed demon, absolutely blazing through the tests. But on the other end of the spectrum, you had BQskit. It was a full 2 orders of magnitude. That's 100 times slower than the baseline. I mean, that's just a massive difference in speed.
But hold on, speed isn't the whole story, right? When you look at the quality of the circuits,
The story totally flips. Ticket, which is slower, often came up with higher quality, more elegant programs. It's the clever specialist. And that really highlights his central conflict. Meanwhile, Qiskit was the reliable workhorse. It was the only SDK that actually managed to complete every single one of the transpilation tests, which makes it a really solid baseline for comparison.
So who's the winner? Well, nobody and everybody. I think the single most important takeaway from this whole thing is that there is no single best software. It's not that simple. Performance is this really complex landscape of trade-offs. Do you need it fast or do you need it perfect?
And hey, don't just take my word for it. The researchers themselves put it perfectly. The entire story of quantum software right now is all about this quality versus time trade-off. It's not about picking the best tool, it's about picking the right tool for the job you need to get done. And you know what? Nothing shows this trade-off better than this chart right here. Just look at the estimated time to run the entire suite of tests. Stack, our speed demon, could get it all done in about 3.5 hours. Trickit, the quality-focused one, would need almost 5 days. And BQSKit, nearly 3 weeks. This is that quality versus time trade-off in the starkest terms imaginable.
Okay, so let's zoom out for a second. Why does any of this matter? Why is putting software through a grueling fitness test so important for the future of quantum computing?
First, you have to get this. The point here is not to crown a winner and a loser. It's not a competition like that. The real purpose is so much bigger, and it's something that helps the entire community.
See, by creating this transparent, open standard, Benchpress lets everyone see how we're doing and track progress over time. It gives developers a roadmap to find the bottlenecks in their own code and fix them. For users like me, it's a guide to picking the right tool for the job. And at the end of the day, making these classical brains smarter and faster is what pushes all of us closer to the ultimate goal we're all chasing, practical quantum advantage.
And all of this leaves us with one final big question to think about. As we're building this bridge to truly powerful quantum computers, we have to keep asking ourselves, to solve the world's hardest problems, what's actually more important? Taking the time to craft the absolute perfect quantum plan, or getting a pretty darn good one really, really fast? For now, it seems the answer is, it depends. Thanks for tuning in.